All right, so now we're going to go ahead and get into some of the details. We're going to talk about the first line of immunity, the second line of immunity. We're going to get into AMPs, IFNs, complements, pro-inflammatory cytokines, phagocytes, right? How that process looks, natural killer cells, and how do they get rid of infected and cancerous cells, and then inflammation and fever. So we're basically going to get into the innate immune system with this particular section. So again, what is innate immunity? We're just saying this is going to be protection in general from a lot of different pathogens. So there is no specificity. It is just, hey, we're protecting ourselves from all sorts of stuff. This is going to be our kind of first response. It's very fast. It's not specific. And it's going to include things, again, like the neutrophils, the macrophages, the monocytes, the dendritic cells, the natural killer cells, the eosinophils, the mast cells, and basophils. So long list. Some of the things we're going to do with this is things like inflammation as well as fever. And we have two lines of defense that are part of the innate immunity, and that's the first and second line. First line being barriers, second line being the first level of immune cells. So let's talk about that first line of defense. How do we create a barrier between us and pathogens? One of the big things is your skin. Your skin is one of your best lines of defense, as well as your mucous membranes. They're going to provide two different types of protection, mechanical and chemical. Now, mechanical protection means that we are physically protecting, we're creating a physical barrier that the pathogen cannot get through. So this is going to include like your epidermis in your skin, the mucous membranes inside of like your mouth and whatnot, saliva, mucus, cilia, things of that nature. And then the physical, like the different liquids or solids that we use or that we excrete that can basically flush out bacteria or pathogens as well. So things like defecation, urination, tearing up, so crying, mucociliary clearance, so like the mucus and cilia in like your trachea, kind of sweeping things up and out, vomiting. These are all different things that could, flush some sort of microbe, flush some sort of pathogen out, right? Because if you notice, all of them, what they all have in common is that there's some sort of substance that is being projected out of the body in some way. So it's a physical removal. We also have our normal microbiome. These are just like normal, healthy, non-damaging flora, so bacteria and whatnot that protect us against colonizing of pathogens. And the reason why this kind of helps us, like these are basically like the good bacteria. The reason why this helps us is that think of it like a neighborhood. If you have a street full of houses, how do you keep a bunch of like squatters out of those homes? You have good neighbors, right? You have people living in the homes. It's really hard to try to squat in a house if someone's already living there. So the normal flora, they're physically taking up space. They're on the skin, they're in the gut, they're wherever, and they don't cause us any harm. They don't even have to necessarily do anything for us physically, but they're taking up space that a pathogen could otherwise inhabit. So if your street of houses is empty, there's nobody living in the houses, pathogens or squatters could easily come in and take up space, right? Same thing in your gut. If you didn't have any bacteria living there, pathogens could easily come in and take up that space. But if you have every house occupied with good neighbors, right, with people who are taking care of the house, and all that, then it's the same thing as having the healthy bacteria taking up that space that pathogens can no longer access. We also have chemical protection. So this is going to be through antimicrobial secretions or just changes in things like pH that are harmful or not productive for pathogens. So on the skin, we have things like sebum and cerumen. Cerumen is going to be wax. So sebum is like the oil that your skin produces. Cerumen, this is like your earwax. These have a low pH, so they're a bit acidic. They're going to be hostile to a lot of bacteria. We have lysozymes, which are enzymes we find in a lot of fluids like sweat, saliva, milk, tears. These are going to break down the cell wall of a lot of bacteria, so then the bacteria will be destroyed from that. And then in places like the vagina and the stomach, we have a low pH from acid, right? Because this is going to kill off a lot of bacteria. It's going to destroy a lot of toxins. So places like the stomach, right, with the gastric juice, and the vagina are going to be a low pH as well to help provide that protection. And if you take a pause here, you can look at the, the breakdown of the picture here on the side. But I think I covered pretty much all of the first lines of defense with the skin and the mucous membranes. Getting into the second line of defense, this is where we're getting into the soluble factors in the cells that are going to very quickly respond to an infection right as it happens. Basically, one of those barriers, let's say like the skin, has been breached, a pathogen has gotten past the first line of defense. So let's say we got a cut, right? We've gotten through the skin, now something like a pathogen can get right to our bloodstream. So what can we do in our second line of defense to protect if something like that happens? We have antimicrobial proteins, or AMPs. We have complement proteins. We have cytokines like interferon. We have cytotoxic cells like mast cells. We have phagocytes like neutrophils and macrophages. We have natural killer cells. And then we have a couple different processes like fever and inflammation. So let's talk about each. Let's go into the antimicrobial proteins. Again, these are these little proteins. They're going to have these charged amino acid residues, so they're hydrophilic and hydrophobic. They're going to basically form a pore or a hole in the cell wall of different types of cells. So bacteria, viruses, fungi, things like that. And this is going to cause what's called osmolysis. Basically, they form an opening and fluid can flood inside of that cell, breaking it open. Now we have alpha defensins and beta defensins. Alpha defensins are made by neutrophils, natural killer cells, Paneth cells, right, that we find in like the small intestines. And then the beta defensins we find with epithelial cells in the skin and the mucosae and immune cells. So you can think of alpha defensins as internal, beta defensins being more external in a way. We also have the complement system, or the complement protein system, or sometimes called a complement membrane attack. This is a bunch of plasma proteins, about 20 plus of them, that will find pathogens and promote inflammation. So when it comes to inflammation and the destruction of bacteria, they're also going to form a pore cell wall, so another hole, right? Basically punching a hole in that cell wall or the envelope, which again causes osmolysis. So fluids can flood in, and then that cell is burst open because the fluid pressure being pushed out on the membrane. We see a lot of these being produced by the liver and then thrown into the plasma of blood. They are preformed in the plasma in the interstitial fluid in an inactive form, and then proteolysis will activate them, right, when the system's activated. So basically they're hanging out in this off state, right? They're turned off. And then once they're activated, they're turned on, and they're going to go and form these complexes, right, to punch holes into something like a bacterial cell. Now we're going to get into our interleukins, which are the cytokines. So these are pro-inflammatory cytokines, meaning these ones are going to promote inflammation, right? These are coming from things like macrophages and monocytes. So their job is to make inflammation happen. So interleukin 1, 6, 8, and TNF alpha. Let's go into interleukin 1. This is going to activate the macrophages, so we can turn the macrophage on. It's going to activate the vascular endothelium, basically for increasing vasodilation. This is going to lower blood pressure, and because we're doing that vasodilation and whatnot, it's going to basically open, like kind of create more space between those endothelial cells, so that the immune cells can go from the bloodstream to the tissue. So something like a monocyte can move from the bloodstream past the endothelial cells of a blood vessel into the tissue and become a macrophage. This can also cause fever, right? And also make you more sensitive to pain as well. Interleukin 6, this is going to promote the B cell activation and antibody production, also can induce a fever, and it can induce the production of more neutrophils as well. Interleukin 8, this is going to help move neutrophils to the infection site. So it's going to serve as a beacon or a signal so that neutrophils can move to the appropriate site. And then TNF alpha, this is also going to activate macrophages, also is going to activate the vascular endothelium and what we call increased vascular permeability. So again, lower blood pressure, we're seeing that vasodilation come in. So this is where we can have those monocytes travel from the bloodstream into the tissue. So you see how interleukin 1 and TNF alpha are kind of working together to create a situation where monocytes can move into the tissues and activate into a macrophage to provide us some protection. We also have interferons. This is a group of cytokines that respond to a viral infection. Basically, they are going to help cells become resistant to a viral infection. So basically the name interferon is that it interferes with viral replication, right? So it will, if we look here, right, the virus gets in, right, into the cell is now infected with a virus. I know this picture's really blurry, but the cell is infected with a virus. This cell, though, will then produce interferon, which the neighboring cells will receive that signal, and now our cell can, this healthy cell can react and go, kind of be on the lookout, like, okay, there's a virus around here. I need to be aware that I need to block that virus from getting in and infecting me, right? Of causing the cell to produce viral particles, right? So that's what interferon does. It interferes with a virus's ability to infect a new cell. We also have the phagocytes. Again, these perform phagocytosis, which is basically an engulfing of a pathogen or something that's not supposed to be there. So it's going to engulf that and then destroy it. And so this is going to be used by things like neutrophils, monocytes, and macrophages. And there's 3 different phases. There's the chemotaxis, adherence, and ingestion. Once we've gotten through this, we have a phagolysosome that's basically going to, basically a lysosome, which has digestive enzymes, is going to fuse with the vesicle that contains the microbe, the like bacterial cell or whatever, and then those digestive enzymes are going to break that, basically shred that pathogen, shred that bacterial cell, and then we can just, get rid of anything that we destroyed. So let's go ahead and talk about those 3 processes. And we're going to start with number 1, which is chemotaxis. This is what we call directional kinesis, basically meaning this cell's going to move, right? And it's going to move in response to a chemical signal. Here we have some sort of cytokine, some sort of chemical signal. The cell is going to detect that chemical signal, and it's going to move in the direction where that chemical signal gets stronger. So it's almost like a beacon, like the cytokine is like a beacon, and chemotaxis is the movement of the cell towards that beacon, right? Towards that cytokine, wherever it's in the most dense or the highest concentration, right? That's what we mean by chemotaxis. It's detecting a signal and then it's moving towards that signal. We also have the natural killer cells. These guys are lymphocytes that go after, they don't have the same membrane molecules that the T and B cells have. Their job is to kill cells that are infected or cancerous, but there's no specific manner. So they're not going after infected cells that have a specific virus. It's any virally infected cell. And so how they do this, we can as a natural killer cell, we can release interferon, which is, again, going to make a cell resistant to viral infection. It's going to provide protection to a healthy cell against a virus. We can also use perforins, and you think perforin, the name alone, if something's perforated, there's holes. So this is going to be stuck into a plasma membrane, and it's going to create a hole or perforate the membrane, which again causes osmolysis, causes that cell to flood and then break open because there's so much fluid pouring in. And then granzymes, these are going to take the nucleus, take the DNA from the target cell, and then digest it. And this is going to trigger apoptosis, or a programmed cell death. So the natural killer cells, they're going to release interferon to protect healthy cells. And then if a cell is infected or cancerous, we can use perforins to break the cell open, and granzymes to destroy the DNA and cause the cell to break down in a controlled manner. We also have inflammation. Inflammation in the short term is a protective measure. It is an important measure to allow certain cells not to get to a certain area wherever that pathogen is. It can be somewhat problematic if it's left unchecked. So, but it is a normal part of the immune response. And so let's go ahead and talk what inflammation is. Basically, some cells have been damaged in some way, whether it's a microbe, a physical agent, so a physical injury, a chemical agent, right? Something has damaged cells. And we have 4 main symptoms that are hallmark signs of inflammation, and that is redness, pain, heat, and swelling, right? And the reason why we get these ones is because the stages of inflammation lead to these symptoms. Number 1, vasodilation and increased permeability of blood vessels. This means that more blood is going to be coming to the area wherever this damage has occurred. That's going to lead to the redness as well as the heat, the swelling, the pain, right? So you think about it, if you have an increased flow of blood to an area, that area is going to swell because there's more fluid. That blood carries body heat, so it's going to feel warmer. That increased fluid is going to put pressure on things like free nerve endings, which means pain, and the redness, right? Because again, we have blood cells coming there. We also have phagocyte migration and entry. So because we have vasodilation and the permeability increasing, blood cells like the monocytes are able to move from the bloodstream into the tissue. And then clearance, right, where we have those cells either using the complement proteins or using phagocytosis. The cells that are going to be part of the inflammation process include the neutrophils, the monocytes, which then can become macrophages, the basophils that become mast cells as well. And then they are going to be using things like the pro-inflammatory cytokines, things like prostaglandins, and the complement proteins. Now, when the phagocytes, when they engulf microbes, they will die off. They can't do this forever. And when they do that, we have a pocket of dead phagocytes. So we're basically a pocket of dead white blood cells and the tissue that's damaged around it. And this is where we get the formation of pus, right? So pus is that collection of white blood cells that have already done their job. They've already phagocytized something and killed something, but they have accumulated in that area. So if we look at everything kind of in order, right, we have something to trigger it, right? We have some sort of wound, right? That wound is going to be detected by things like mast cells. We have the activation of the macrophages and the complement protein activations. These mast cells then are going to release pro-inflammatory cytokines, and this is so that we can recruit more immune, I guess we'll say tissues or immune cells to the area. We will then go through vascular vasodilation, and we'll increase permeability so that cells, immune cells in the bloodstream can move to the tissue that has been damaged. The cells that are moving towards the damage are using chemotaxis, right, and diapedesis, right, the neutrophils, the monocytes that are coming from the bloodstream into the damaged tissue, where they will then phagocytize and kill whatever pathogens they can find, and then they will release more pro-inflammatory factors to amplify this, to keep this going, and to increase the response so that we can get rid of this pathogen. We don't want a weak response. We want a strong response to be able to fully eliminate, or at least try to fully eliminate, or at least control a pathogen until the adaptive immune system can come into play. Now we've mentioned fever, right? You may be thinking, what's the point of a fever? Why do we do this? And what even is a fever? So generally speaking, a fever is 38 degrees Celsius or higher, which is about 100.4 Fahrenheit. This is going to be when you get some sort of infection from a fungus, from a bacteria, or you're exposed to their toxins, as well as some viruses. And the things that are going to kick a fever on are called pyrogens, right? They're fever inducing, because pyro, we think like hot, right? So pyrogens are going to induce a fever. They're going to cause a fever. So pyrogens, right, made by a pathogen are going to trigger interleukin 1 in the macrophages. This is going to get to the hypothalamus, and the hypothalamus is going to raise the body temperature in response. So pathogen has some sort of marker on it that we detect that's going to turn interleukin 1 on, and then your hypothalamus receives that interleukin 1 signal and goes, oh snap, turn on the heat. And the point of it is that the higher body temperature can actually inhibit some microbial growth, and it can speed up some of these other reactions to make the immune response faster and stronger. So that's the whole point. The fever is there to try to help us. We're basically trying to burn out that microbial growth. Obviously, if a fever is too high, right, then that's something we need to be concerned about, because the person's own healthy tissues can be damaged by it. But a low-grade fever or whatever is not unheard of, right? So we look at what's going on, right? Some sort of macrophage is brought, it takes on this bacterium. There's some sort of endotoxin produced by that bacterial cell, and then it's going to degrade. It's going to release those toxins, which then this cell's going, oh snap, these toxins are there. I'm going to release things like interleukin 1 and TNF alpha. Those cytokines get into a blood vessel. Those cytokines go through the bloodstream up to the hypothalamus, and the hypothalamus goes, oh snap, turn up the heat, right? Turn up the temperature so that we can produce a fever to try to burn out these microbes.